All right. Since we have a holiday on Monday, we won't see each other for a little bit, so I wanted to record a quick video to give you some help with the homework. There's kind of two parts here. The first part is going to be a direct help with the homework, and then second part I'll get into a little more advanced theory related to derivatives, and you can safely skip that. That's just for if you're interested. So um, we've been looking at problems recently where we're combining an autoencoder with a neural ODE. So in this figure, I don't know if there's a way for me to do a pointer here. Look like it, but uh, the idea is that we train an autoencoder and the neural net that's estimating the dynamics of the neural OD at the same time, right? So we start here in the upper left, data space. That's just my original X vector or Y or whatever you want to call it, my states in my original just regular data space. I pass that through the encoder portion of my autoencoder, and now it's in what we call the latent space, right? This is what we've been calling Z. It's a lower dimensional space. Um, and yeah, and from that low dimensional space, the hope is that perhaps this is easier, much faster to solve. So now we pass this through our ODE solver in this reduced space, and now that gives us solutions at different time steps. And now we can pass it back to the decoder to move it back to our original space, out of the latent space back to our original space. And then this paper here is one nice paper showing this technique and adding some parameterization so that you can add parameters that you learn for the ODE to help it generalize better. The paper we're going to be replicating for this current homework is this one. A related idea of using an autoencoder with a neural ODE, but it also has this physics loss function that we're going to use, and that's kind of analogous to what we did before with pins. Except for in this case, we don't have a residual per se, but we do have some consistency equations that we'll derive and look at today. So here's a diagram from their paper. I slightly changed as I'll point out here in a second, but the idea, again, same idea is that I've got some uh, dynamics that are potentially either high dimensional or difficult to solve, maybe computation expensive or unstable. And by projecting it into this lower dimensional space, perhaps it'll be easier to solve faster. So we can go through first the encoder as I go from, and I'm just here, I'm just encoding the initial condition. So that says x0, right? So I just take the initial condition x0, encode it. That gives me z0. That's my initial condition in this lower dimensional or latent space. Pass that through the neural ODE, right? So propagate that in time. We're learning the dynamics in this latent space. And this gives me z hat. I changed this in the paper. It says z underscore capital T, indicating maybe the final time step, which is fine conceptually, but in the paper and as you should, you're going to use the whole z vector. So this z hat is my z at every time step from 0 to t, depending on my discretization. And then I decode that. So now I have a solution in this latent space, pass it to the decoder, gives me back a solution to my original ODE problem that I'm trying to solve, but I solved it in this reduced dimensional space. So compressed it, so to speak, solved it, decompress. And here's portions of the loss function. This is the data loss. This first part, prediction loss, that's just the same loss function that you'd be used to from any sort of data-driven process, meaning that this x hat that I get out here at the end, I want that to match the trajectories that I have x. So I've got some data, right? I've got some data of my dynamics that I have these trajectories in time. So x is a trajectories, x is a function of t. So I've got potentially many trajectories. I don't know what the dynamics looks like, perhaps. And maybe it's hard to train in this high dimensional space. And so, yeah, this is one possible approach to do that. And then I have a second term, which is that I need my encoder and decoder to be effective. So in other words, so phi is the encoding, psi is the decoder. If I take my x, all these trajectories, I encode them and then decode them, I should get back something very close to my original state x, or those trajectories. So that's the reconstruction loss. So I want both those things to be low, right? I want to have a good autoencoder, and I want to have a good representation of my dynamics. So how would we do that? This is pseudocode here, so don't type this exactly as is, but this is kind of the idea. I created a file for you that generates data depending on how many collocation, or well, we'll get to collocation, how many data points you want, training points, testing points, and so on. And the X vector happens to be of size. The first dimension is the number of batches. The second dimension is the number of time steps. And the last dimension is the size of X, right? So like how many states does X have? And so I'm getting all the batches, all the dimension of X. And I'm just getting the first time step, right? So this is my initial condition for X. I pass that through my encoder. It gives me an initial condition in Z. And remember, encoder, this is just going to be some neural network that you've defined. And now I pass it through the ODE int function that we've been using, just the same one we've been using for our other neural ODEs as before. And this ODE func, again, is also a neural net. Also remember pseudocode, I didn't write out like time steps and things. This is not the exact thing, but this is the idea in pseudocode. I pass in the ODE function, which is some neural net that I'm trying to learn, while I'm also learning the encoder and decoder. Z0 is that initial condition, and I can integrate forward in this latent space. And now I have my trajectory Z hat, and I decode them. So now I go back. Decode is also, again, another neural net, which typically is just the mirror image of the encoder. So whatever layers and nonlinearities you use in the encoder, you just kind of do those backwards in the decoder. And so now I've got an estimate of my trajectories in my original high dimensional space. So I've got two loss terms. One is the mean squared error. I want the X hat that I predicted to match my X. And I also want my autoencoder to be effective. So if I pass in X, and notice this is not just passing in my initial condition X, I'm passing in all the trajectories X, encode, decode. I want that to give me a good representation of my original X. One thing to be careful with, you're going to need to use a permute here. So for example, think about the shapes. Make sure you go look at the shapes. Again, I told you the shape of X, and that's written in the file I provided, but n batch by number of time steps by number of X points, state of X. When you do the integration from Z0, right, we've changed dimensions and now we've done an integration, so we're going to add more points in time. It's not going to be the right shape you want directly to give it into the decoder, so you're going to want to use a permute function, not a reshape function. You should understand the difference between those, but permute, just like if I've got, let's say it came out and I don't remember, so I'm just making this up, but like number of time steps, which actually probably is what it is, number of time steps, number of batch, number of X, and I need to switch those, that's permuting, right? I want to change those indices. Okay, and so that would be, this would be what I call, I mean, to call something, well, this would be kind of a standard neural ODE with an autoencoder, but in this paper, we're going to add a physics loss term, and that's going to help us to do better in the absence of you know, or I should say better than we would with just the data that we have. So we can perhaps extrapolate better or have better accuracy for a given amount of data. And so in physics informed loss part, here I'm borrowing a figure from their paper. This is the same figure we just saw, and I'm just showing you part of it that's relevant here. And I'm just pulling out a few terms, and I'm going to do a little bit of math here. So remember that dx dt is f of x. That's just our definition. That's the dynamics. And those are dynamics that we could just evaluate. We have some sort of function here, if we can, right? Like say we have a function. And z, and so in this example problem where we do have a function f, it's high dimensional and we're saying it's hard to solve and we want to maybe have a low dimensional representation. And z, remember, is a function of the encoding of x. So phi is the encoder. So again, I'm not writing anything new here, just writing these equations out again because we're going to use it. So if I take derivatives, I take dz dt. By the chain rule, that's dz dx times dx dt. And dz dx, that's just the derivative of my encoder, right, with respect to x, so d phi dx. And dx/dt by definition, that's just f, right? That's my dynamics in the high dimensional space. Okay, so that's fine. Let's leave that there for the second. And then let me write down another equation here that isn't new, but again, look up at our dynamics. So remember, we have this neural ODE, initial condition comes in, we integrate, we get z. But inside there, we have this function h, which just defines the dynamics in the low dimensional space. It's analogous to f, but f is in the high dimensional space, h is in the low dimensional space. So h is just this function that tells me the derivatives, right? How do my dynamics evolve? Well, not really how they evolve, but what's the rate of change? So if I take derivatives of dz dt, which is the same thing I did before, but now with this other equation, I have h of z, and z, remember, is just an encoding of x. So now I've got two equations, both where I calculate dz dt. So for consistency, these need to be equal to each other. So now I have another equation that I can use to ensure consistency. And the thing to notice here, this is why this is kind of, we call this like this physics loss term. It's analogous to kind of what we did with the pins, meaning I'm not running a solver here. I don't need to run any ODE solver. This doesn't depend on my data points. I'm free to choose any, again, what we call collocation points. So I can choose these after the fact anywhere in the domain. I choose these X collocation points. And so let's look at the right-hand side, for example. I just choose them anywhere. They don't have to correspond to data points. They could, but I could put them anywhere. I run them through my encoder, right, which I have, and I run them through H, which, again, these are both functions I just am learning through a neural net. And I get a value on the right-hand side. And on the left-hand side, f of x, those correspond to me evaluating my original function, which I have, the data generation function I have that gives you that when you choose collocation points, it evaluates f. Notice I'm not solving the dynamics. Remember, f just tells me the derivative, dx dt. It tells me this function that perhaps is hard for me to solve the ODEs for, is expensive to solve. Like a typical use case for maybe an autoencoder with the neural ODE might be these large unsteady PDEs, because if I take these PDEs that are unsteady in time, I can change them to a whole bunch of ODEs. So it's a very high dimensional problem, but I expect that, all of these tons of dimensions corresponding to all these grid points, let's say, these mesh points, uh, is way more dimensions than I need to capture the relevant physics. So I want to code it into this kind of low dimensional space where I can solve it and perhaps even learn something about low dimensional representation. But anyway, so I have this f of x that I can call. I'm not solving it. I'm not integrating in time. I'm just evaluating it. And those are done beforehand. When I choose the collocation points, I can do that at the same time. So those are provided in the training data. And then, so the main new thing I need here that I don't already have is I need d phi dx, which is the derivative of my encoder with respect to x. Okay, so yeah, so then, well, here's a picture of that from the paper. So again, collocation points, x hat, free to choose. I need to pass them through my encoder. And notice here in the middle, I'm just calling h. I'm not doing an integration, no ODE solve. So this is faster, just calling it. And these are separate points that don't have to correspond to my data points. So I have some extra terms I can have here. So this is what we're calling the physics loss here. It has these two terms. The first is the one that we just derived, right? I need that equation. We moved everything to one side, set it equal to 0. So I need that to be, I need to minimize that. And then I have a second term here that is just like the first one. I want the autoencoder to function well, and I'm just giving it more information. I'm saying, here's some more sample points. These aren't data points, but these are just collocation points. Here's some more collocation points. If you encode them and decode them, I want to get back, as close as possible, my collocation points. So again, in pseudocode, what does that look like? I choose these collocation points, X, and when I do, I'm choosing a number, I'm kind of maybe randomly or maybe strategically, depending on how I want to extrapolate, or where I want my model to, perhaps maybe it's not doing as well and I need more points somewhere. I'm choosing these X collocation points. At the same time, I'm getting the corresponding F, right? That's just that function, my high dimensional space. So I pass those through my encoder. I get Z collocation points. And now I call my ODE function. Notice it's not ODE integral. I'm not integrating it. This is just the function. This is just and so it has two things here, right? Because remember the OD function that I integrate has t comma y is what we've called it, right? It's a time and then a state. And the time is irrelevant for us in this problem, right? Because we don't have a time dependence. You could have added that if you think there was, but like most ODEs, there's usually not a direct time dependence in the derivatives. So you can pass anything in there, it's not used. And so I'll just call that ODE function, which is a neural net, and I get z dot, right? I don't get the trajectory. I'm just getting the derivative z dot that it's learning. And then I have these two loss terms. And the last one is again, same as before, take the collocation points, encode, decode, and try to get them as close as possible to my original collocation points. And then this first one, the physics one, that's the one we just talked about. So z dot, I got ready. That one's easy to get. This dz dt, that's the harder one. So that's the one I'm going to spend a little time and show you actual code or a very similar example for actual code. Okay, so yeah, let's go on and look at the dZdt. So remember, the dZdt that we need here is this term that we derived. It's dZdx times dx dt, and the x dt part I already have. That's just my high dimensional dynamics evaluated my collocation points. That's provided when I generate collocation points. And in general, that's just me just evaluating whatever function I was trying to solve to begin with. So dpdx is the new thing, and this is not really that hard because we've done this before, right? You've taken derivatives when we did pins, and this is really the same thing with the encoder. Just a slight difference here because we have multiple outputs. I just wanted to go through that real quick. So let's do that. I'm just going to create an example here, and it's going to be like similar to the one you have, but not exactly. I'm not going to do the exact same problem, just kind of a small one. So let's create a really small problem. Let's say the batch size is just 4, the number of points in my high dimensional space is 3, and the number of dimensions in my low dimensional space is 2. Okay, so yeah, just a toy problem here. So let's create some random x points, so batch size by nx. Let's create some z points. Actually, I'm going to compute them, so I'm just going to initialize them for now. And then f, these are my dynamics evaluated at the high dimensional space, so they're also nb by nx. So these get generated at the same time, x and f. So let's just start with that. So I choose a number of collocation points, I get x and f, and now I need to pass them through some encoder. And instead of writing an actual neural net, I'm just going to make up some really simple function to compute an x given a z. So let's just say here's a z, and this is not an efficient way to do that, but I'm going to do it in a for loop to emphasize clearly that every data point is independent of every other one, right? If I take in an x and I pass it through my function and I get my z, and I take a different sample in the batch, those don't affect each other, right? Like choosing this other data point number 2, it doesn't affect my output of data point number 1, right? And so I'm doing this in a for loop to really emphasize that, and that's important for how we compute the derivatives. I'll talk about it again in a second. So I'm going through one element in the batch at a time. So remember, this is the batch dimension, this is the z dimension, and I'm just going to multiply it by some matrix, like, kind of like analogous to a linear layer, so to speak. And then I'm going to add some sort of nonlinearity, otherwise all the derivatives will be the same. This is not one we'd normally use, right? But this is just a squared, but that's fine. It doesn't matter what it is. I'm going to make up some a. Again, that's not really relevant to the problem. It has nothing to do with like the a that in the problem. It's just example. So all of this code here, irrelevant. All it just means is that I just need some function that goes from x to z, and in your case, that's going to be a neural network, right? Encoder portion. So here's my encoder, and let's just evaluate it. So this would be the way that we've done this before. If I have X, I pass it through this function, an encoder, and I want to get derivatives, and we've used torch autograd.grad, and so you probably know how to do this, just want to be careful here. The only thing that you have to remember with grad is that, remember, a gradient has one output, right? Like that's what a gradient means. It's not a Jacobian. We can use a Jacobian function. We haven't done that before, and I will show that if you decide to stick around. It's not necessary. In this case, we only have two outputs, and in the problem that we're doing, we also only have two outputs. So you can do this manually with grad, and that's what I'm going to show you first because it's something you already know. Probably not the most nice way to do this because we're kind of, you know, well, we might as well use like a Jacobian function because that's what we're really after instead of doing it one at a time. But here, it's not necessarily any less efficient this way because the Jacobian, you still under the hood has to do it once per each output anyway. It's just perhaps a little cleaner and not as manual looking here. But let's do that. So remember, Z has two outputs. Z is going to be of size NB by NZ, but I have two states here. So I got to do it for one state at a time. I can do all batches at a time, and this is the part that we did before. It's maybe not obvious. I know we talked about it, and I'm going to talk about it again here if you decide to stick around for that second optional part. And I know we talked about it in class, but that's where because a batch, every data point is independent of every other data point. They don't, right? If I add the second data point, it doesn't change my output for the first data point. So because they're all independent, I can actually do them all at the same time if I'm clever about it. So this is, remember, grad takes outputs and then inputs is X. So I'm trying to get dz dx, right? This is that dz dx term. And then this is that grad outputs option. I need to put in, this is where I put in the ones. I'll explain that again. I've explained this once before, but this has to do with the fact that because these are all independent, the ones tells me, as I'll show you, that I can sum all of these derivatives. I know this isn't going to make sense unless we think about it. So actually, I'm not going to explain it here until you get the math. Just remember, this is exactly what we did before. We put ones in. It needs to be the size of my output. And I'm going to need to retain the graph. What's it called? Yeah, retain. Because we're going to need derivatives of this. Sorry, not retain graph. It's create graph. Create graph also does the retain for me. And remember that this returns a tuple for a tuple of inputs, but I only have one input because I could have done other things here, right? But I don't know, other inputs. Since I only have one, I just need to pull out the first one. And this is going to give me dzdx, but it's only giving me dzdx for the first entry of x, right? Because, or sorry, I said x, z. Z has two variables. So I'm going to initialize dzdx v of size, number of batches, number of z variables, number of x. So dzdx is a Jacobian really of nz by nx, and then I have a separate Jacobian for every data point in the batch. And in this first one, I'm doing it for the first z, right? With respect to all x's, because that's okay. Gradient can be respect to as many inputs as you want. And I'm doing all the batches at once by doing this little trick with the ones, kind of like we did before. So this is only giving me the zdx for the first z, and I have to do this again. And this is why I say this is maybe a little less elegant because I've got the same size, doesn't matter. But anyway, so that's, yeah. So this is all you really need to know for that. I'm going to show you two other ways, but going on beyond here is optional. If you just need help with the homework, this is all you need because this uses what we've done before. We did the same thing before. We put ones here, and we had different inputs. Like you took the derivative of say u with respect to x, or u with respect to t, or ux with respect to x to get the second derivative, and so on. Oh yeah, one more thing I need to do because I'm taking to respect to x, I need to have this track that. So I'm going to say requires grad equals true. Yeah. Okay, so, oh, no, sorry. This is not, I need to show you one more thing because remember, this is dz dx, and I want dz dt, so I need to multiply by dx dt. I have that. That's f. That's this thing right here. So I need to multiply dz dx times f. But dz dx is number of batches times number of z's times number of x, and f is number of batches times number of x. So I need to make sure I multiply them properly. I want to multiply it. This is a matrix vector multiply. It's an nz by nx times nx, and I need to do that separately for each batch, right? They're kind of separately being multiplied. So one way to do this is there's a batch matrix multiply. So let's just open up the docs real quick. Pull this up here. Look at that. So that we'll do the right thing. I could do it in a loop, but that's going to be inefficient. So I want to call this function. So what does it say? It says if you have an input that's b times n by m, so b is a batch size, times b times m by b by m by p, the output is going to be b, right? So I'm doing it once per batch, and it's doing an n by m matrix times an m by p matrix. So, right, those inner dimensions got to match, and I get an n by p as expected. So this does what I want. The only problem is, what do I have? I have b by z by x, and I've got b by z. And so this is not going to be happy because it says I need that p dimension. So the way we can do that is we got to kind of play with the dimension a little bit. So I want to multiply dz, dx, and f. And if they're all the right sizes, that's all I would do. And I get dz, dt, right? Because that's this expression here, right? dz, dx times this f. It's a matrix multiply. It's really a matrix vector multiply. But so what do I need to do? This z is batch by x, but I need it to be batch by x by 1. So I can use the unsqueeze, and now I have to tell it which dimension to add add a dimension on. So I've already got something in dimension 0 and something in dimension 1, and so I need to add something in dimension 2. Now doing that, this f is going to be batch by x by 1. And so that's great because I've got batch by z by x times batch by x by 1, which will give me a batch by z by 1. So now it's batch by z by 1. Yeah. And it will turn out that when I want to compare this to is just going to be batch by z. So I want to drop that last dimension. So we're just going to squeeze it here at the end. So that now it's batch by z. Yeah, because later the thing we compare to the dz/dt that we get from go back here. And we're comparing it to this thing that gives my ODE function. It's going to be z by d. So you could have done one or the other. You could have expanded this one. Either way, you just always want to check when you're comparing two things. Make sure they're the same size. If you're doing mean squared error and they're different sizes, weird stuff can happen. It might broadcast and give you weird stuff. Anyway, okay, so that is really all you need to know for the homework. I'm going to go on a little more advanced stuff because I just want to show you some alternate ways to do this and kind of review why are we doing this one thing again? What does this mean? So again, a little more advanced. Definitely you can stop here, but I'm going to keep going a little bit. So let me briefly review this reverse mode AD. So remember reverse mode AD or backprop, it's kind of the case where I have one output. I have some operation or some function, whatever you want to call it. X comes in, Y comes out. And when I'm going backwards, a Y bar comes in and I need to compute X bar coming out as I'm going backwards. And bar just means the derivative of some eventual thing. Here I'm calling it L, say it's a loss function with respect to whatever that variable happens to be. And so if I want X bar, by definition, it's dl dx. And by the chain rule, that's dl dy, which is Y bar, times dy dx. So in matrix vector notation, this would be X bar transpose equals Y bar transpose times J, where J is the Jacobian dy dx. So reverse mode AD does what we call these vector Jacobian transpose, or sorry, vector, a vector Jacobian product, right? So vector is Y bar, J is the Jacobian. I'm multiplying them together. And this allows us to do a number of different things in this one way. So when we do these vector Jacobian products, I don't actually ever need to form J because I don't actually care about J. I care about X bar. But what if I do care about J? In this case, I want J, right? I want dy dx. That's what I'm actually after. I'm not actually after X bar in this particular example because I'm not doing like this backprop back to find the sensitivity relative to the loss. All I want is what's the derivative of this encoder, right? Like that's this. I know the y and x don't match what we were using before, but just, some operation output with respect to input. So in a picture, right, this matrix here on the right, that's a Jacobian. In general is not square, right? So this would be like, say I had two outputs y and three inputs x. Maybe that's what I want. And these y bars now, I'm free to choose them to be however what I want. And this is actually what that grad outputs thing is. If I put something in there, I'm telling it what to put in these y bars. And normally, like the way we talked about backprop, is I'm going all the way through. And so I start at the end, and y bar has a nice meaning because it's going to be L bar. And so it's just going to be, ones and zeros. So one way I can get well, I'm just rewriting the same thing again. If all I have is one output, y is just a scalar, then, this simplifies. There's just one y. And obviously what I probably want in y bar is just one. I don't need to put it. So if all I have is a scalar output, you don't have to use that grad output thing. It's optional. It knows, oh yeah, there's just one output. What you get is a gradient. You can see it's dy dx1, dy dx2, and so on. And that's, what I'm calling is that grad function. But if I want a Jacobian, well, I can only get this, one row here at a time. Um, so what I could do is I could put in that Y bar thing. I could do it twice. I could put twice because I have two outputs, but in general, once, just once for every output. I put a one and then zeros for everything else. And if you see if I do that vector matrix multiply, that vector Jacobian product, this top one here, I get the first row. So I get the derivative of one output, y1, with respect to all my inputs. But now I have to do it again, and I have to switch, I have to put a one in the next thing. And in general, I have to repeat this for every output. But now I get a Jacobian by putting these ones and zeros appropriately. But our test case is a little different here. This is not a general output y and a general output x. Often I'm going to have these data points or a batch, or it could be the entire data set, doesn't matter, but they are independent in the sense that the output here, y2, has no dependence on x1 or x3, right? And here I put them up top to illustrate these parentheses up top to illustrate these are different data sets. X could be a vector and y is a vector, but they have no dependence, right? X1 does not influence Y2 at all. So if I was to look at this case where let's say I've got all these different batches of data going in, and again, they're potentially vectors, and Y is also potentially vectors, but just to keep this a little simpler here in this example here, let's just say Y is just a scalar. If it's not, I have to repeat it for each Y, which is exactly what we just did. So notice that I get this kind of block matrix. Each of these is potentially a block because X is a vector or really a tensor in general. But all of these off diagonal components or off diagonal blocks are zero because dy1 does not depend on x2 or x3 or x4 or anything else. They're all zero. So only these diagonal blocks remain. So if I put in all ones here, what I get when I multiply through is I get just those diagonal components left because everything else I know is going to be zero. So instead of doing 1, 0, 0, 0, 0, and then calling it again 0, 1, 1, or 0, 1, 0, 0, 0, and doing that n, ny times, in this case, only two times. Well, actually not two times. It would be for every batch, I'd have to do that. So, if I've got or every data point. So if I've got 1,000 data points or 1,000,000 data points, I'd have to repeat that a million times. But in this case, if I put all ones, I can get all the derivatives of the entire batch in one shot, one pass, right? Because I know that there's going to be all these zeros. So by putting the ones, this is just going to do the right thing for me, right? So I get here on the right all those gradients that I want. So this is why we put all these ones. So this is a vector Jacobian product. I'm just writing that again. We saw that we could use this many ways. So the interpretation we used it, we didn't actually put in a y bar that represented like a derivative with respect to some loss far away. We used it to say, oh, I could put in a one strategically to get different rows in my Jacobian, or I could put all ones in the case where I've got like this diagonal structure. And so here I'm writing it maybe in a more general way where it's a vector Jacobian product where V is just something I choose. It could be a y bar, and that then the output would be interpreted as an x bar, but it could be something else. Right? And so if I write out some of the terms, I'll write out a few of them. This is just another way to see this. Remember that in our particular case, and sorry, I wrote these as subscripts instead of superscripts, but all these off diagonal ones would be 0. So you can see if I put in ones for all of my v's, I get the terms that I want. Another way to see this is, as I've written this out and you look at the bottom here, I can see that my vector A is the derivative of V transpose Y with respect to X. And Y is potentially some vector, but when I take the V transpose Y, that is a scalar, right? Like, so Y is a vector and V is a vector. So when I take the dot product of them, I get a scalar. So now I'm taking the derivative of the scalar with respect to X. And so this is now a gradient. So if I have so what this means is either y needs to, if I call grad, y needs to either just be a scalar, or if y is not a scalar, which is in our case it's a batch, I need to provide this vector v that says how are you going to transform it into a scalar for me? Like how do you want me to weight them? And in this case we're saying weight them with all ones, right? Sum them all up. And that works in this case because I'm only summing along the batches. I didn't sum along the different sorry, this is confusing because it was z's. I didn't sum across the different z's because they're two separate ones. I can't sum those, but I can sum across the different batch data points. So I had to do it twice for each output z, but within a specific z, I could do it for all the batches at once. And so I put the v's as ones, everything else is 0, and I only am left with the ones, or I can get all of them at the same time instead of doing a 1, 0, 0, because I've got this diagonal relationship. So yeah, I could have, instead of calling it gradient multiple times, why don't I just do a Jacobian? And so we could do that. We could, if we look at this kind of equation that we came up with here, V transpose Y dx, could say, well, that's what I'm after in this case. Instead of, yeah, so I could compute the Jacobian of my output Z, where I want to sum along the batch dimension, because remember, I want all these V's to be 1. So we could do that in code here. We could say there is a Jacobian function, uh, and I got to be a little smart about it because I want to sum all my batches when I do this. So let's see, it's functional.Jacobian. It's a little different because I have to give it a function here. So I'm going to have to give it a function. I'm going to call it, it needs to be different functions. We'll call it fsum. What I take the derivative with respect to. So grad, I put outputs and inputs. Here I give a function and inputs. And then I need to do all this same to create graph stuff. So I'm going to want to differentiate this. So fsum, I'm just going to write a function just to make this clear. I'll instead of being a one line, I'll just write it out. But all that's going to do is I'm going to take the sum of this function x, but I'm going to sum it along the batch dimension. So remember, x is of dimension nb by nx. But I'm going to sum all the batches, and that works because when I take the derivative with respect to x, the derivative of f1 with respect to x2 is 0, and with respect to x3 is 0, and the only one I get left with is the derivative of batch 1 with respect to x from batch 1. Okay, so this is a little trick here. I'm doing that sum. So this V transpose Y, where, you could think of this as a sum, because it's all ones. I'm just summing along the batch dimension. So now if I take this Jacobian, yeah, this is equivalent to this up there. So this gives me dz dx, call it 2 since it's a different one. And that's going to be the same as this one here, or sorry, I'm still going to have to multiply it by this stuff if I want to get dz dt, but this one is will give me exactly this. Well, except for not quite. The order is a little different, so I got to permute. Let's just check it real quick. Jacobian, Yeah, it's going to be derivatives of this f output with respect to x. Let's just look at that quick. Let's make this easier. So let me just run this. Create some data. Just run all this stuff. Run this one. Autograd.functional. Okay. So this is not going to be the right size. So let's see. Here's dz dx. It's of size 4 by 3 by 2, 4 batches, and each one is a Jacobian of n nx by nz, or sorry, nz by nx. And if I look at the new one I just calculated, not going to look the right size. Okay, so what is the size of that dz dx2 dot shape? It's 2 by 4 by 3, so it's nz. This is nz by nb by nx. And that's because it doesn't, all it's doing is saying, okay, what's my output? F sum, if I put in F sum of x, what's the shape of that? It's just nz, right? Because this is summing over all the batches. So this just gives me something that's of size z. So two outputs here. So it says, yeah, that's my output. And it's a well, it's a generalized Jacobian here because this is relative to this matrix. Output relative to input. And the size of the input is nb by nx. So the end result is nz by nb by nx. But I wanted it to be the size of this one, which was nb by nz by nx. So I want to swap these two dimensions. So I'm going to permute. So I want this one to be first. So this is my 1. I want that to be the first thing. And then I want z to be the second thing. So that was my 0. And then I want x to be the last thing. So that's 2. Okay, so let's try that. dz dx2. So if I took these and subtracted them, yeah, they're the same, right? So I get the same answer either way here. Okay, and then one last thing, there's one more way I could do this. Perhaps sometimes better. And so what I have to remember, what I actually want here is not dz dx, but I want dz dx times dx dt. And so what I've done so far is I've created that Jacobian dz dx, and then I multiplied it by this vector dx dt. But what I could do is a Jacobian vector product. So in reverse mode, you get this vector Jacobian product, the vectors on the left side. Jacobian vector product is what forward mode does. Okay, so in forward mode, I could provide this vector, and then I don't have to form the Jacobian at all. As I'm going through and computing them, I'm doing these vector products as I go, and so this is going to be more efficient that way. So for example, instead of computing dz/dx and creating this matrix and then multiplying by all these f's, remember dx/dt is f, I can do that as I go, right? Like, so for example, this is that first line. This is analogous to that y bar we saw when it was like, how do I weight them? It's just that it's on the other side here. It's we're weighting these, we're weighting each column as opposed to weighting each row. So this is what forward mode does. And PyTorch has an implementation of a Jacobian vector product. It actually doesn't use forward mode. It uses a reverse over a reverse. But let's just try this out. So this is torch.autograd.functional.jvp, Jacobian vector product. So I give it the function that I want. That's this original function, okay, that I want to differentiate. I want to differentiate with respect to x. So that's this Jacobian portion, right, dz dx. And now I have to give it the vector. What's the vector that we're going to be multiplying by? It's just f. And then I need to create graph equals true. And it also actually returns 2 items. So let's look at that. Returns 2 items. It returns the function output and the JVP that I want. And I don't care about the function output. That's just, see, I don't know what that is. So I just want, no, I want the second thing. I want this JVP. So this is going to give me dz dt, this thing. So I don't have to do this batch matrix multiply. It's giving it to me directly, and it's going to do it in general more efficiently, not necessarily in this case because it's a reverse of a reverse, which is clever, but not necessarily the most efficient. But let's just try that. So let's compare dz dt minus dz dt2, and you can see how those are the same, right? So this is the thing I actually want is dz dt. So in other words, I could replace, these multiple lines here, or these 3 lines plus this one with this one liner. It's potentially more efficient. Like I said, not necessarily in this case. It's clever. There's this web page, if you're interested in this, has a nice little derivation about this reverse over reverse. Again, the traditional way to do this is forward mode, and you can do that actually if you look through this docs here. It says that, hey, this is not necessarily the most performant way. You could use kind of our lower level APO, or you could use this thing. There's torch.func JVP. I didn't show this one because it was just a little less cleaner in the syntax, but totally doable. In practice, for this problem and for the size of the batches data, I didn't really see any significant difference in computing time here. I just wanted to show you these things. For those of you who plan to do more in this space, that sometimes you're gonna have more outputs. You're not gonna want to write this or try to loop this. You're gonna want to do Jacobian or Jacobian vector products, things like that. Okay. Yeah, no, that's more than enough. So yeah, see you later.